Okay, in this video I am going to discuss on the rotational spectrum of polyatomic molecules. By saying polyatomic molecules, we mean the molecules having three or more atoms. Okay, molecules having three or more atoms. Three or more atoms. So a triatomic molecule can be considered as a polyatomic molecule, or a molecule having four atoms can be considered as a polyatomic molecule. For example, we are going to consider first the linear molecules, linear polyatomic molecules. Why we are considering linear polyatomic molecules? Because the problem of the linear molecules are much simpler compared to the non-linear molecules. That is why we are starting with the linear molecules. Examples of linear polyatomic molecules are OCS. Okay, this is an example, OCS. And another example is HC triple bond CCl. Okay, chloroacetylene. This is a polyatomic molecule, linear polyatomic molecule. And OCS is similar to OCO, or carbon dioxide, but carbon dioxide cannot be studied here because this carbon dioxide does not have a dipole moment, a permanent dipole moment. So carbon dioxide will not give microwave spectrum, but OCS will give microwave spectrum because it has a permanent dipole moment. Okay. Similarly, if you are considering acetylene, HC triple bond CH acetylene, this also does not have a permanent dipole moment. Therefore, this also will not give microwave spectrum. So we can conveniently consider HC triple bond CCl as a linear polyatomic molecule having showing microwave spectrum. Okay. And let us take the example of OCS, that is oxygen atom. Then it is connected to the carbon atom. Okay, then carbon atom is smaller than the oxygen atom, you can see in this figure. And then the carbon atom is connected to a sulfur atom. Sulfur atom is much bigger than the carbon, and at the same time oxygen also. Okay, and therefore this is oxygen, this is carbon, and this is sulfur. Okay, and the center of gravity of this molecule lies somewhere here. It is not on the carbon, and it is lying somewhere left to the carbon, or somewhere right to the carbon. It means it is lying somewhere close to sulfur. Okay, because sulfur is the heaviest atom in this heaviest of these three atoms. Okay, so this is the center of gravity. And now we can consider some axis in this molecule. For example, let us consider this axis. Okay, this is one axis. This is actually the internuclear axis. If the molecule is rotating about this internuclear axis, its moment of inertia will be 0. Let me call this as axis A. Then the moment of inertia about this axis is equal to 0, because during this rotation the atoms are not changing their position, so the moment of inertia will be approximately equal to 0. Okay, but if we are considering another axis, an axis like this, the axis passing through the center of gravity like this, let me call this as the axis B. And above this axis, if the molecule is rotating, then all the atoms will change their position in space, right? All the atoms will be moving in a circular path if the molecule is rotating about this axis. Actually, this axis is in the plane of the board. Therefore, the molecule will make an end-over-end rotation perpendicular to the plane of the board, right? End-over-end rotation, end-over-end rotation, end-over-end rotation about the axis B. Okay, and there will be a moment of inertia corresponding to that, that is IB. Okay, and now I can consider another axis. That axis is actually passing through the center of gravity, and that is perpendicular to the B axis and the A axis. So let me call this as the C axis. Okay, and this C axis, you can see that it is perpendicular to the plane of the board, right? So if the molecule is rotated about C, then the molecule will be rotating in the plane of the board itself, right? That is also an end-over-end rotation, and so there is again an end-over-end rotation about about Z, and the moment of inertia corresponding to that is IC. Okay. So here we can see that in both cases, that is in the case of IB and IC, the molecule is making end over end rotation, end rotation, either in the plane of the board or out of the plane of the board, right? In either case, it is making an end over end rotation about an axis passing through its center of gravity, and therefore IB and IC will be equal, right? Okay, IB is equal to IC. This is the case. But at the same time, IA is equal to 0. So IB is equal to IC, not equal to IA in a linear polyatomic molecule, and at the same time IA is equal to 0. Okay, we are considering this type of a system. Okay, so a linear polyatomic molecule's state can be defined as IB is equal to IC, not equal to IA, and at the same time IA is equal to 0. Okay, so if we are considering the energy of this system, the energy EJ, actually I am expressing energy in terms of centimeter inverse. That is why I have put epsilon J. So epsilon J is equal to Bj into J plus 1 minus dj square into J plus 1 the whole square. Okay, plus etc. If we are considering the and harmonicity of the vibration, you can consider more terms here, but if you are limiting this to the enharmonic vibration, then you can say Bj into J plus 1 minus dj square into J plus 1 the whole square. Okay, centimeter inverse. So that is the energy expression in terms of centimeter inverse. So that is the same expression that we already constructed for the diatomic linear molecule. Okay, so here also it is a linear molecule. Even if the number of atoms are changing, it is a linear molecule. Therefore we can consider this as a rotor, and since we are considering this as a rotor, we can use the same equation here. Epsilon J is equal to Bj into J plus 1 minus dj square into J plus 1 the whole square. But remember here that from the B value here, right? From the V value, you will get a moment of inertia value I, right? Because you know that B is equal to H divided by 8 pi square IC. This is B. So if you get the B value, then you can calculate I value here. But the B value you can get from the spectrum itself. So if you are taking the spectrum of the OCS molecule, then you will get the corresponding B value from the spectrum of the OCS molecule. But from that you can calculate the I value. But which I value are you calculating here? We were talking about IB, IC and IA. Which I value you will be getting here? You will be getting IB or IC. Okay, because IA is equal to 0 here. That will not be reflected in the spectrum. So the I value that you are getting from the spectrum will be equal to IB, or it is equal to IC. Okay, so that is what you have to understand from here. But in the case of a linear molecule, that was not a case, that was not a problem there. Okay, in the case of linear molecule, we just took I. Actually there what we are taking I is nothing but IB itself. So if you are considering this as a linear molecule, okay, here also you can consider this as the A axis, and then this as the this one as the B axis, and this one as the C axis. Therefore here also IA is equal to 0. In the case of diatomic linear molecule also, IA is equal to 0 and IB is equal to IC. Therefore, the I that we obtained there is also equal to IB or IC, but we didn't mention there. That's all. Okay. Actually, the moment of inertia that you are devising from there is nothing but IB. Here also the same case. The not moment of inertia, the B value. The moment of inertia. Okay. The moment of inertia that you are getting from there is the IB itself. And then we have to note some points. First point that you have to note is that here in the case of a polyatomic linear molecule, okay, the moment of inertia of a polyatomic linear molecule, for example, triatomic molecule, it will be greater than the moment of inertia of a diatomic molecule. Okay, so moment of inertia I of polyatomic molecule will be greater than the moment of inertia I of diatomic molecule. So what will be the result of this one? Why the moment of inertia is greater here in the case of polyatomic molecule? Because we know that I is equal to mu r square, right? Mu is a reduced mass. In the case of polyatomic molecule, mu will be higher. And what about R? R is the distance between the end atoms. For example, if you are considering OCS like this, R is nothing but the distance between the oxygen and the sulfur. This is R. Okay. But if you are considering only carbon monoxide, it will be like this. Only two atoms are there, carbon and oxygen here. Here also carbon and oxygen, carbon monoxide. Okay, so the R here is the distance from carbon to oxygen. So this is R in the case of diatomic molecule. Which R is greater? In the case of polyatomic molecule, that R will be greater because we have an additional bond here, that is a carbon sulfur bond. Okay, so additional bond is there, so this R is greater here. So R is also greater, mu is also greater in the case of polyatomic molecule. Therefore, the moment of inertia I will be greater in the case of polyatomic molecule. Okay, so I in the case of polyatomic molecules will be greater than that in the case of the diatomic molecules, and therefore B, you know that I and B are inversely proportional. B in the case of polyatomic molecules will be less than the B in the case of diatomic molecule, right? And therefore, what will be the consequence of this in the spectrum? You know that the ideal distance between the lines in the spectrum is equal to 2b. 2b is a separation in the spectral lines, right? Separation in the spectral lines. So this 2b separation will be less in the case of polyatomic molecules because b is less there, right? So separation of the spectral lines will be less in the case of polyatomic molecules when we are comparing with the diatomic molecules. Okay, that is what we can get there. For example, in the case of a diatomic molecule, the B will be in the range of 10 centimeter inverse, something like that. Okay, if you are taking many examples of diatomic molecule, B will be in the range of 10 centimeter inverse or something like that. But at the same time, B in the case of triatomic molecule, it will come something like 1 centimeter inverse. Okay, so if we are considering the B of the triatomic molecule, it is much less than that of the diatomic molecule, and therefore the separation between the spectral lines in the case of polyatomic molecules will be smaller than that in the case of diatomic molecules. Okay, that is the first thing that you have to understand here. And now the second factor that you have to understand here, the second factor to be understood, and as in the case of the diatomic molecule, this polyatomic molecules should also possess the dipole moment in order to show the microwave spectrum. Okay, dipole moment is must. Polyatomic molecules also should have the dipole moment. So this is a criteria for any molecule to show the microwave spectroscopy. Okay, so that its dipole moment should be a non-zero value. For example, you know that OCS is a polyatomic molecule or triatomic molecule. It has a permanent dipole moment because in both sides of the carbon, two different atoms are attached. They have different electronegativity values also. Therefore, OCS has a permanent dipole moment. Therefore, OCS is microwave inactive. Microwave active means it will give rotational spectrum. But if you are considering the similar molecule OCO or carbon dioxide, then carbon dioxide does not have a permanent dipole moment. Therefore, this is microwave inactive. Carbon dioxide is microwave inactive. But if you are considering, if you are substituting one of the oxygens with another isotope, for example, if you are substituting one oxygen with O18, okay, CO. This is O16 and this is O18. So will it show microwave spectrum? Will it show microwave spectrum? The condition for a molecule to show microwave spectrum is that it should have a permanent dipole moment. Here you have to understand that by making an isotopic substitution, okay, that is not going to bring any change in the bond length. That is, the carbon O18 bond length will be equal to carbon O16 bond length. The isotopic substitution does not bring any change in the bond length. And at the same time, the electronegativity of O18 is equal to the electronegativity of O16. Okay. So what will be the result? We have carbon here, then O18 and O16 are attached at both sides of the carbon. O18 is here, O16 is here. And this distance is equal to this distance. Okay, both will have the same bond length. And at the same time, this atom will have the same electronegativity as like this one, even if they are different isotopes. So both atoms are placed at equal distance at both sides of the carbon, and at the same time both are pulling the electron towards its side with the same strength. Therefore, what will be the result? It will not have a net dipole moment. So even if there is an isotopic substitution, the dipole moment is not changing. Therefore, carbon dioxide with O18 substitution, O18 isotopic substitution is also microwave inactive. Okay, microwave inactive. So this is the second thing that we have to understand. And one more point that we have to note here, the third point. After that I will close this lecture. The third point that we have to note here is that in the case of a diatomic molecule, for example in the case of carbon monoxide, right, carbon monoxide, we calculated the bond length of the carbon monoxide, bond length. So microwave spectroscopy was a tool to determine the bond length in a diatomic molecule. What we got there, in the case of a carbon monoxide molecule, in order to calculate its bond length, we took its spectrum. From the spectrum, we understood the 2B. From that one, we understood B. From the B, we calculated moment of inertia I, and we equated the moment of inertia as mu r square. Then we substituted for this mu, that is the reduced mass of the carbon monoxide, and from that one we calculated r, and from that one we calculated r square, and from that one we calculated r. Okay, so starting from the 2B we reached r. It was a straightforward calculation in the case of a diatomic molecule, and this r is nothing but the bond length. So we can directly get the bond length by analyzing the spectrum of a diatomic molecule, the microwave spectrum of a diatomic molecule. But what is the case if we are measuring the spectrum of a triatomic molecule like OCS? Here also we will get a B value. But from that B value we can reach an R value. But what is that R value? That R value is the distance between the first atom and the last atom. This is the R value. Okay, and that is not the bond length. This is the distance between oxygen and sulfur. We actually wanted to get the oxygen carbon bond length and carbon sulfur bond length. Okay, and from the microwave spectroscopy we will get only the sum of these two bond lengths, that is the OC and CS bond lengths. And we have no method, we have no direct method to calculate back the individual bond lengths involved here. We cannot calculate it directly. So that is a limitation of the microwave spectroscopy in the case of the polyatomic molecules. We cannot calculate bond length directly. But we can overcome this difficulty by a proper method. Okay, what you have to do is that we have to take the microwave spectroscopy of the carbon microwave spectroscopy of this OCS molecule. Okay, and from that we will get a moment of inertia I value. Okay, and now what we can do is that instead of O16 here, we can substitute with the O18. So we will get a new molecule, okay, and we again we have O18 here. We again do the microwave spectroscopy of this new sample with the oxygen substituted with the O18, and from there we will get another moment of inertia value. Is it the same as the first moment of inertia value? No, because the mass is changing here, right? O18 മാസ് ഡിഫറൻ്റ് ആണ്. മാസ് ചേഞ്ച് ചെയ്യുന്നതുകൊണ്ട് നമുക്ക് ഇവിടെ നിന്ന് കിട്ടുന്ന മൊമെന്റ് ഓഫ് ഇനർഷ്യ വാല്യൂ ഡിഫറൻ്റ് ആയിരിക്കും. ഈ മൊമെന്റ് ഓഫ് ഇനർഷ്യ വാല്യൂ ആണ് നമുക്ക് ഡയറക്റ്റ് ആയിട്ട് എവിടെ നിന്ന് കിട്ടുന്നത്? നമുക്ക് സ്പെക്ട്രത്തിൽ നിന്ന് കിട്ടുന്നത്, അല്ലേ? അപ്പോൾ രണ്ട് മൊമെന്റ് ഓഫ് ഇനർഷ്യ വാല്യൂ നമുക്ക് കിട്ടും. ഈ രണ്ട് മൊമെന്റ് ഓഫ് ഇനർഷ്യ വാല്യൂസിനെ നമ്മുടെ കമ്പയർ ചെയ്തുകൊണ്ട് നമുക്ക് വി ക്യാൻ ഡിറ്റർമൈൻ the bond lengths, individual bond lengths in this molecule. That is possible. Okay, so even if the microwave spectrum does not give a direct information about the bond lengths in a particular sample, we can get the bond lengths by making some proper experiment. Okay, and what we can do here is that we can make an isotopic substitution and measure the microwave spectrum of both samples, and from the data obtained from both samples we can calculate the individual bond lengths present in these molecules. Okay, so that is the third point that you have to remember. Okay, and here I have explained the microwave spectrum of the polyatomic molecules, and I have not gone for the lengthy derivations here, because the same equation that we got in the case of the diatomic molecule is applicable here also. Okay, so now we know about how the diatomic molecules from how the rotational spectrum of the polyatomic molecules will look like. Okay, and I hope you understood. Thank you for watching, and stay tuned. If you have any doubt, please don't hesitate to ask me. You can comment in the comment section below, and thank you for watching, and stay tuned.